So the demo file is a PDF. I've used Matlab to generate this PDF. I have on purpose not given you the M file to sort of discourage you from copying and pasting. So study it, make sure that you understand the way that things are done, but avoid copying and pasting from this document to solve your own problem. When you are solving your own problem, try to sort of rediscover or come up with your own solution. Okay, you can look at the functions that I used, check the documentation in MATLAB for those functions, and make use of them that way. Okay, so don't just blindly take things from here and copy and paste and hope they work. Okay, so let me go in here. Okay, I need to increase the font size. All right, I can do this in two different ways. I can either go over the code that I've written already, or I can start from scratch and write code. Start from scratch. Okay, I'll do both. I'll start from scratch, but I also refer back to here and keep it in line with what I have. More data basics. Demo 2, this is going to be what I'm going to work on from scratch. I'll leave the other one open to refer back to it as needed. Okay. So in this demonstration, I'm going to make use of the data for the Wisconsin breast cancer data set. So this UC Irvine machine learning repository is a popular data set for machine learning problems. It has a large number of data sets. You can see how many. It says 463. So these are sort of toy data sets that people use when they have a new idea for a machine learning method. They go in and see how well their new idea performs on these data sets. And then they can therefore claim that their idea works better than some of the other ideas that people have used on these data sets. Okay. So we are going to search for breast cancer. Oop. This web page now lists an overview of the data set. So it's a multivariate data set, meaning it's composed of multiple columns. Attributes are real numbers. The task is classification. So sometimes you may also have tasks that involve regression, meaning we are trying to predict an actual number. Here we are going to try to predict yes or no, or 1 or 2. We're not going to try to predict a real value. Okay. The number of instances, that means the number of samples. We have 569 samples in this data set. Number of attributes is 32. We have 32 columns in the data set. Are there missing values? No. Meaning for every sample, there's a value for every attribute. For some of the other data sets, there may be missing values. For some samples, they may not have certain information. The area is live, so that's just, it's a biomedical problem. The date donated is 1995. This is the date that this data set has been made available to the public on this website. And there's about a million web links coming back to this web page. You can read information about this data set and information about attributes and any relevant papers from this data set. Okay. I'm going to go into data folder, which will contain files for this data set. I'm going to use the terms data set or database to refer to this particular collection of data. Okay. There's a file with .data extension. That's going to be our data itself. There's another file called .names, which will give us information about the data set. Let me look at .names first. So it's a text file that you can look and read. If you scroll down, it will have the names of the attributes here. Okay. Let me go back and open this in a new tab, and also open the data in a new tab. So in this particular data set, the data file is just numbers. It does not contain the names of the attributes. So you can sort of combine the two files when you are interpreting them. In some of the other data sets, they may give you an Excel file where the first row contains the attribute names. Or they may give you a text file where the first row contains the names of the columns. For this particular one, the data and the names are in two different places. All right. So we need to download this file, right, before we can make use of it. One idea is to copy and paste it to a file on your computer. So I can highlight everything, go to Matlab, and edit my new data.text or .data, whatever name you want to give. So there's my data. I'm going to save it, and now it's available. I can make use of it on my computer. Okay. But we're not going to do that. We would like a way to automatically download this file from our code. That way, our program is more reproducible. There's less human intervention. So me copying and pasting or me downloading from my browser is sort of a human intervention. It's not repeatable. So we would like to write our programs as so that they work as with most automation as possible and with least human intervention as possible. So when I take this file should contain everything I need to reproduce the results. How do I save the file? I can use a function called web save in Matlab to take a URL and download that into a file. The URL is the address of the web page. I'm going to provide that first. And then the name of the file would be, let's call this Wisconsin.data. When I run this function, let me do it in the command window. It's the other way around. It requires me to give the file name first and then the URL next. Okay. Now it's saved it. I can open it up and look at it. Okay. But we're not going to use this method either for this class. What we are going to use is a folder that I shared with you on Dropbox. You should have already received a Dropbox share link on your email, on your Dropbox, with your Dropbox email. Accept that share, and what you will get is a new folder in your Dropbox after you have accepted the share. That is called bmes.ahmed, and it contains this @bmes folder. Okay. So this folder should already be available to you after you've accepted the Dropbox share. Find out where this is and copy the address. Or go to your Matlab and add a path to that folder. So I'm going to click on set path, this link right here. And then I will add a new folder. I will then browse into the folder that I shared with you. So you would do that. Wherever your Dropbox is, you would have to go to that bmes.ahmed folder that I shared with you. Okay. Once you find that folder, select it, and then you can save it so that next time you start Matlab, it starts off with this folder added to your path so that you don't have to repeat this every time you open Matlab. Okay. So save and then close. Click on save and then click on close. I already have it on my path, so I don't need to do that. Okay. All right. So what is in that folder? That folder is a collection of functions that I have written to make homeworks more uniform, so that you guys can focus on the machine learning problem and not have to deal with these file downloads and making sure that you don't re-download something, and it makes grading easier as well. Okay. So this BMES is a MATLAB class file. You may not have encountered classes in MATLAB before, but it's essentially a collection of functions. Okay. I will show you how to use them in this lecture. One function available is called bmes.downloadURL. Okay. It wants me to provide the URL first, and then the data file after that. I'm going to get the file back. I'm going to remove that. The second argument is optional. If I don't provide the second argument, it's going to use this first one. I don't have to worry about where it is saving. What it will do is actually not save it in the current folder. It'll save it in a temporary folder on your computer, or it's going to save in a data folder on your computer. So it will automatically decide where to save. So it looks like I have a problem here. I have previously saved it, but it's not detecting. Oh, sorry. I know what's wrong. All right, so I fixed, and let me, for good measure, also do this. Okay, so it's done. The changes that I made are already synchronized on your computer. You don't have to re-download my BMES library. Okay, so this function call downloads that file and makes it available on this folder on your computer. It's going to make it available on a different folder. Okay. Next time you run this, it will not bother re-downloading. So if I go in the subway, I don't have internet anymore, this code will still work. Okay. Okay, so it will download it once. After I download, I have to read it. I have to load it into Matlab. This file is a comma delimited file. The entries are separated by commas. There are different functions in Matlab that you can use to load this file. The one that's most convenient is called read table. Okay. Read table. Let me give myself more room here. Read table looks at a file and it will automatically decide how to load that file. The extension for this file is .data, and Matlab does not know how to interpret a file with the extension .data. So the error that we get is saying that it has no predefined way of understanding what the .data file is. So if it were an Excel file, it would already know. If it were a text file, it would already know. But .data is not as conventional, so it doesn't have rules for this type of file. So we're going to have to help it along a little bit and say, read this file, and since you cannot decide what type of file it is, I'm going to tell you what it is. It's a text file. Okay. When we rerun this, it gives us, it loads the data and prints out in a command window. Let's save it into a variable. So this T is now a table object. It is not a numerical matrix. It's a table object. Okay. Objects have additional functionalities than just numerical matrices. One thing you can do with a table object is to use indexing like you do with matrices. So let's select the first 5 rows and the first 4 columns from this table object. It shows us the names of the attributes, followed by a table of values for each column. These variable names are not really the variable names that we would like to see. We were hoping to see things like the clump thickness and the cell size and things like that, right? But there's nowhere in this file that those variables are listed. So this file only contains numerical data. Matlab did not really have any chance to learn what these columns are. If the first line contained the names of the variables, Matlab will automatically discover those names and use them instead. But since it did not, it will instead show us var1, var2, var3, which are just automatically generated names. So again, we're going to have to help it along a little bit again. We're going to say, by the way, here are the variable names. And to do that, we are going to go into the object, go into its properties by saying .properties. And then within properties, we're going to say .variable names. If I just hit enter, it shows me the current variable names. I have to replace them with a collection of the variable names that I want it to use. The variable names that I want it to use are these, which I extracted previously from the other file, from the names file. This one right here. So I went through this document and extracted these names and give them shorthand replacements. I called the first one ID, so that's the sample code number. I called the second one thickness, that's the clump thickness. Okay. Cell size uniform is going to represent the uniformity of cell size, and so on for the remainder of the attributes. So one restriction in Matlab is that the names of the attributes should not contain spaces or any non-alphanumeric characters, which is why I don't have spaces in my variable names here. So I'm going to place this in here, and I will tell the table object to change its variable names to this new variable set. After I do that, if you make a selection, rather than seeing var1, var2, now you see the correct labels for your variables. What are the other things I can do with the table object? In addition to using numerical indices, I can use strings, I can use text or cell array of indices, which you cannot do with a regular Matlab matrix. Right? So I could say, show me the thickness. So select the thickness column. If you want to select more than one column, you need to enclose your column names into a cell array. Show me or select the ID and thickness columns. All right. So very convenient. You don't have to go through your variable names and see which one is it. Is it the second one or the third one that represent the thickness? That job is going to be done internally for you by the table object. When I make a selection, let me go back to thickness. I can make a selection so that the new selected result is itself a table object, or I can make it so that I only get the numbers and not the table object. So if you are interested in just those numbers without any additional functionality, you can use curly brackets to index your table. So if I replace the parentheses with a curly bracket, the result is not going to be a table object, it's going to be a numerical vector. The reason I would want a numerical vector is to perform mathematical operations, such as using the mean to find the average. Cannot be done if the input is a table object. So if you make a selection and use parentheses, this result becomes a table object. The mean function does not know how to handle it. So we have to go back and make sure that we are extracting the numbers, just the numbers themselves, without making it a new table object. And the mean function will work with the numbers rather than the table object. Make sense? So if you need to perform operations with the numbers, make sure that you use curly brackets to extract the numbers. Okay. If you need to maintain the tableness of your selection, then you would use parentheses to make the selection. Okay. Next, let's look at a box plot visualization of the data. A box plot is a convenient way of looking at two groups. In this case, we're going to look at benign and malignant groups. And let's look at the thickness for each sample. So for benign samples, we would like to create a box representing the distribution of the thicknesses for the benign samples. For the malignant, we're going to create a box plot that summarizes the distribution of the thicknesses for the malignant samples. If there are any outliers, they will be shown below or above the box. Box plot will automatically detect any outliers and not make them part of the boxes. It will also show us these whiskers, these additional lines to show the extent of the data beyond the median or the criteria that it uses to draw the box. Okay, so the spread of the thickness values is displayed in a box plot. For the box plot, we need to provide the values, all thickness values, and also what group they belong to. So we need to provide two columns, the thickness values and a group information. Let's say the thickness is 3, it's from group number 2, the benign group. Thickness is 5, it is from the benign group. Thickness is 7, it is from the malignant group. Okay. So we need to provide this column that we extract from data and also this column that we extract from the data. Make sense? Let's extract those two columns. That column means all rows of the data, and I'm using a curly bracket so that I get just the numbers and nothing else. These are my thicknesses. I will also get the class labels, which are 2 for benign and 4 for malignant. So these are my two columns. I will then give these two columns to a box plot function. Let me work in the command window. The thickness column and the class labels. Let me put this down here so you guys can see it better. I'm going to create a figure and place the figure here. So it sits at the bottom. And you guys can look at the top, which is not blocked by the heads of people sitting in front of you. Okay. All right, now you're good now. All right. So we have to provide the thickness column and the group column, and this is the plot that the box plot will generate for us. The plot doesn't contain the labels, so we did not provide to the box plot function what 2 represents and what 4 represents. We have to read the documentation for this data set, and we will learn that 2 represents benign and 4 represents malignant. And now we have to tell the box plot function what they are, so that rather than showing 2 and 4, it will display the correct labels. To do that, you would look at the documentation for box plots, which I've already done for you, and you provide an additional argument labels, followed by a list of labels that you would like to produce. So now your plot will contain benign and malignant as the 2 groups. And of course, you need to always put your X labels and Y labels. So my X label represents the class. My Y label represents the thickness of the data as I'm showing. Okay. So this figure tells me that the malignant samples overall have larger sizes. They are thicker. Okay. Their thickness values are higher than the average thickness values of the benign samples. But it also shows me the spread of them, right? So there are some samples that are malignant that are not as thick. Okay, so overall, they are thicker than benign, but there are some samples that don't fit this pattern. There are also some patterns that are benign that happen to have large thicknesses. Okay. So that box plot shows you the overall, a summary of the values for the attribute that you're analyzing. Okay. It has not discovered any outliers. Sometimes you may have, let me artificially add an outlier here. Let me add T thickness equals 100. So I will artificially add an outlier. I will go back and create the box plot again. That was too large. Let me make it 20. Okay. So with this new box plot, where I artificially added a sample point that is benign, but it has the value 15. Okay. So with an outlier, you typically don't want it to affect the box that is being created. So if I have a value 1,000 here, the median or the average or the standard deviation of the box would have to be like this to accommodate it. So MATLAB goes through a first step of going through the samples and identifying which ones are outliers and excluding them from the remainder of the calculation. So the box is now drawn without considering that outlier. The box represents all the other samples except for this one. The box plot still shows you the outliers. That way you guys can see. Here's the overall view, overall summary of the samples, and I have some samples that are beyond that, which are not included in that summary. Make sense? Okay. That is the box plot. Next, let's look at the correlation. A correlation is between two variables. So if I look at my data set, I can pick out any two columns and ask how well are they correlated. Each of those columns can be considered a dimension. So let's call this X dimension and Y dimension. You can plot it in 2D if you'd like. The value in your first dimension and the value in your second dimension will represent a point in 2 dimensions. So that's just my first sample. For my second sample, I'm going to have another point right here, let's say. Third sample, another point right there. And the overall layout of the points may be such that they are sort of on a line and they are correlated with each other, right? So they are distributed along a line. Not exactly, but they follow that line. So if they are highly correlated, they will have this pattern. If they are anti-correlated, they will have a pattern that looks like the following. So when one goes up, the other one goes down. That's anti-correlated. Okay. If there's no correlation, they're just going to be all over the place. All right. The correlation value tries to capture this behavior of when one is going up, is the other one also going up? And it's captured in a numerical value that varies between -1 and 1. 1 is perfect correlation, meaning when one goes up, the other one exactly goes up by the same amount, or by a coefficient of that amount. Okay. Again, we have to extract 2 columns, ask the correlation function, tell us what the correlation value is between those 2 columns. Let's look at the thickness and the cell size information and see how well they are correlated. We're going to extract the thickness. That will give me a column. And then we're going to extract the cell size, which will also give me a column. Again, I want the numbers. I don't want them to be a table object anymore. And I will pass this to the core function in Matlab, which will give me a correlation value. So the correlation value between these two variables is 0.51. Okay. When you're looking at the correlation value, you also need to look at the significance of the correlation. Let me call this one R. I don't want to say p-value because let's say p-value of correlation. Okay, because later on I'm going to reuse the p-value for something else. So now, in addition to correlation, we get a measure of whether the correlation is significant. Okay. So you have to consider these two hand in hand. So 0.5 may not be too large of a correlation, but it is a significant correlation. If it is significant, then you have sort of more trust in it. Okay. If this number is large, you typically don't look at this one. So if they are correlated by 0.95, that's a very high correlation. This one will be a very small number. Okay. So most of the time we only report correlation. But to be more complete, you also need to report the significance of that correlation. whether that correlation was, how consistent was that correlation across different samples. Finally, we're going to look at the significance of difference in a variable between two groups. So the question that I'm going to ask is there significant difference in the clump thickness values between benign and malignant samples? Okay. So the way that I'm going to structure the data is going to be slightly different now. I have to go to the thickness values. That's my thickness column. Identify which ones are benign. So that one is benign, that one is benign, that one is benign. Collect them into a benign thickness vector. And then go through, find out which ones are malignant, and extract them into a separate malignant vector. This first vector will contain the thickness values for all benign samples. The second vector will contain the thickness values for all malignant samples. Once I have these two vectors, I'm going to ask whether they are the same or different, or overall, are they the same or different? And the type of there are different types of statistical tests that I can use to answer that question. In this example, I'm going to use t-test, which assumes that the variables are normally distributed. So to identify which ones are benign, I would have to first extract the class. These are the class labels. And then ask which ones are twos. It gives me a logical vector indicating which ones are benign. I'm going to store it in a variable, a logical variable equals that. So these zeros and ones represent which ones are benign. Wherever a sample is a benign sample, I'm going to have a 1 for it. I will repeat the same thing for malignant and ask which ones are malignant. Okay. Wherever I have a 1 here, it's a malignant sample. I can now go to my table, which I will reduce for demonstration purposes. I'm going to reduce the size of this table to be only the first 10 rows, so they fit on my screen. I'm going to repeat extraction of benign, extraction of malignant, and then now go back to my table, index only the benign rows. I'm selecting only the benign columns, getting their thickness information. These are the thickness values only for the benign samples. And do the same thing for the malignant samples. These are the thickness values of the malignant samples. Okay. There was only one malignant sample in the top 10, which is why you only see a single number. Okay. Let me go back and repeat this with the entire data set. Okay. So now I have my two vectors. I can pass them on to the t-test function, which will tell me whether they are different values or not, whether overall one set of values is different than the other set of values, which is done on this line of code right here. I extracted the values of the thicknesses for the benign samples, the values of thicknesses for the malignant samples. So those are two vectors. One is like that. The other one is like that. They don't have to have the same size. You may have different number of samples in each group. The t-test will tell us whether these numbers are different than these or not, these numbers. So if benigns are generally smaller in thickness compared to malignant, the t-test will give us an output that reflects the significance of their difference. I'm going to look at the second output from the t-test, which will be the p-value of the significance in their difference. If this p-value is very small, that indicates that the difference in the figure that you see in the box plot, that difference is significant. Okay? So even though they are separate, right? The boxes are one is above the other, but one of them has a whisker that goes down, one of them has a spread that goes up. So they have overlap, right? But that overlap is small. Overall, we can confidently say that benign samples are thinner and malignant samples are thicker. So this statement is statistically significant. So our statistical test supports the hypothesis that malignant samples are thicker. Make sense? And we base our claim on the p-value, on the smallness of the p-value. You would generally have a threshold for your p-value. A p-value of 0.01 is very typical. So we would say find the p-value and compare it with 0.01 threshold. If it is smaller, then our hypothesis is supported. If it is larger, then it is not. Okay. That wraps up my tutorial for the homework data basics. I will now go over the actual